in today's video I am going to walk you through how to create your own pulse width modulated bass sound. Over the next few videos we will build it step by step, and by the end you will be able to play it using your MIDI keyboard or even your computer keyboard. So let's get started. So you probably remember when we talked about the waveforms, I played a pure square wave and it sounded really hollow and kind of basic. Then we also talked about something called pulse width and the duty cycle. So just a quick recap, the pulse width is a unique property of square waves and you can change it to create rectangular waves, also known as pulse waveforms. And the duty cycle is the amount of high voltage, so when it's a high percentage duty cycle like 80%, the width of the top of the waveform is much longer than the bottom. And when duty cycle is low, say 10%, the top of the pulse wave when the signal is high is short and the bottom width is much longer in a typical scenario. I can use the pulse width knob on the VCO below the frequency knob, and this will change the square wave into a pulse wave. Let's have a look and listen. Unfortunately, this will be steady and not modulated over time, unless I manually keep twisting this knob. And obviously I don't want that, I want it to run automatically. Fortunately, there is a PWM patch point here. So what is a PWM? The pulse width modulation technique is a way of altering the width of the pulse wave, and it's a great modulation effect, especially when we only have one VCO in our setup. For this reason, many VCOs have a dedicated pulse width modulation input, and this is what we're going to use. Okay, we already have our patch from the previous lesson and we're going to use it as our foundation. Now let's set the LFO to about 11 o'clock. So it runs at very low frequency, and the VCO, let's make it similar. Now let's connect the LFO to this patch point in the VCO called PWM. So what's changed? Well, not much, because we also have this little knob here above the PWM, and these knobs are called attenuators and they're used to control the amount and the direction of the signal received. At 12 o'clock it has no effect, so if I twist it to the right, we actually now start letting the sine wave into the PWM modulation for our square wave. You can see there is also like a little vertical lines running down here, and this indicates which patch points work together. So again, this attenuator allows the PWM to work. It controls the strength of this incoming signal from the sine wave, and the PWM influences the square wave, as it can only modulate a square wave type. Now we could turn the attenuator to about 3 o'clock, and you can see in here, you can see on the oscilloscope what's happening to our pulse wave. The purple line is the sine wave from the LFO running very slow. As it goes up and down in voltage range, it modulates the duty cycle of our pulse wave. And let's hear it without this effect. And again with the pulse width modulation. So this is cool, right? It doesn't sound as plain and hollow anymore. But why does this actually happen? Why does it sound different? I want to know everything, so let's quickly have a look. Let's take the small spectrum analyzer and let's run the modulated pulse wave into it. So do you see what's happening? The LFO, by altering the duty cycle of the pulse wave, is constantly adding and removing the harmonics. Let's adjust the modulation amount with our attenuator. Let's increase the LFO frequency to about 12 o'clock, so the sine wave starts running faster and we get a faster modulation effect. Now what would happen if I turn this to, say, 9 o'clock? This way I am inverting the signal, and our attenuator is now called an attenuverter because it's not only controlling the strength of the incoming signal but also inverts the signal. In other words, it flips the polarity of the signal, so the original signal has positive and negative value. Inverted signal will flip these, turning positive values into negative and negative into positive. But for now, let's just focus on our attenuator, so back to around 3 o'clock. And this is our patch with pulse width modulation with a sine wave. Now you know how to modulate a square wave with an LFO, turning it into a pulse wave with changing duty cycle. So try and recreate this patch from scratch and play around with the LFO and the attenuator to explore how you can alter the duty cycle of this pulse wave. You could also try different waveforms of the LFO and see what happens. I like to use sine waves for PWM because of the smooth shape. I get a smooth modulation.